Stretching a simple rubber band actually makes it demonstrably hotter, a counterintuitive physical phenomenon defying expectations. This peculiar elastic property reveals a fascinating, intricate battle between order, chaos, and molecular design. From bundling letters to launching projectiles, rubber bands are ubiquitous, yet their true nature remains largely unexamined. These unassuming loops of elastic material hold secrets of polymer science and thermodynamic principles. They represent a triumph of engineering, making countless daily tasks simpler and more efficient for everyone. Imagine a world without instant elastic tension, without that quick snapback from deformation. Their origin story begins not in a laboratory, but deep within the Amazon rainforests centuries ago. Indigenous cultures first discovered natural rubber, observing its unique elasticity and waterproof qualities. However, raw rubber proved unreliable. It became brittle in cold and sticky under summer heat. This inherent instability prevented widespread practical application for centuries, limiting its true potential. Then, a pivotal discovery transformed this sticky substance into a truly versatile material. The process of vulcanization fundamentally changed rubber's properties, making it resilient and durable. This revolutionary breakthrough paved the way for the creation of our familiar, dependable rubber band. At its core, a rubber band functions due to the amazing behavior of its long polymer chains. Imagine millions of microscopic spaghetti strands, all tangled up in a chaotic, random mess. When relaxed, these individual polymer molecules are extremely coiled and highly disordered. This disordered state is precisely what scientists call high entropy, a measure of molecular chaos. Now, when you stretch the rubber band, you force these tangled chains to straighten out. They align themselves along the direction of the applied pulling force, becoming much more ordered. This action significantly reduces their entropy, moving from a chaotic state to a more organized one. But here is the strangest part. The rubber band asterisk wants asterisk to return to its original disordered state. It's like releasing a spring. The natural tendency is to recoil and become tangled again. This innate drive back to disorder is the fundamental force generating the rubber band's elasticity. Unlike a metal spring, which stores energy in its stretched atomic bonds, rubber stores it differently. Rubber primarily stores energy not in bond deformation, but in its struggle against molecular disorder. This unique phenomenon is known as entropy elasticity, a truly remarkable material characteristic. The entropy change causes the rubber band to get warmer when stretched, releasing latent heat. Conversely, when you quickly release a stretched rubber band, it becomes noticeably cooler. This temperature change occurs because the molecules absorb energy to return to their chaotic state. Think of it as a tiny, reversible heat engine working right there in your hand. But the complexity doesn't end with just simple stretching and contracting movements alone. Rubber bands possess an incredible memory, always returning to their original shape after use. This remarkable resilience comes from the cross-linking of polymer chains during vulcanization. Imagine tiny molecular bridges connecting the spaghetti strands, preventing them from sliding completely apart. These crosslinks provide the structural integrity, ensuring the material doesn't permanently deform. Without these crucial connections, your rubber band would simply stretch out indefinitely, losing its function. Different types of rubber, like natural latex or synthetic versions, exhibit varying elastic properties. Natural rubber, derived from tree sap, offers superior elasticity and incredible tensile strength. Synthetic rubbers, however, can be engineered for specific resistance to chemicals or extreme temperatures. The color of your rubber band, incidentally, often comes from added pigments, not its natural state.
And here's a curious fact. Rubber bands actually weaken over time, especially when exposed to light.
Ultraviolet radiation slowly breaks down those vital polymer crosslinks, reducing its elasticity forever. The principles of entropy elasticity extend far beyond just simple office supplies, influencing diverse fields. Engineers utilize these properties in designing advanced shock absorbers and vibration dampeners. Medical science employs elastic polymers for surgical tubing, gloves, and various prosthetic devices. Even in sports, the performance of shoes and equipment often relies on precisely engineered elastic materials. Think about the impact of a simple elastic waistband on clothing comfort and universal fit. The ability to store and release mechanical energy so efficiently has countless practical applications. Consider how elastic bands are crucial for packaging, securing items, and even postal services worldwide. They provide a low-cost, effective solution for temporary binding, easily deployed and readily available. From artisanal crafts to large-scale industrial processes, their utility remains incredibly broad. The invention of the rubber band itself revolutionized how we organize, store, and transport goods. It allowed for the neat bundling of documents, replacing cumbersome strings or fragile paper clips. This seemingly minor innovation dramatically improved efficiency in offices and factories everywhere. Understanding entropy elasticity provides insights into other soft materials, like gels and biological tissues. It informs research into creating new smart materials that respond dynamically to environmental changes. Ultimately, the humble rubber band offers a profound lesson in the elegant physics of everyday objects. The next time you stretch a rubber band, remember the silent dance of molecules battling for chaos. It's a testament to how deep scientific principles underpin even the most common, overlooked objects. Subscribe for more amazing explorations into the hidden science of our world, and share your thoughts below.